Black holes are among the most fascinating objects in the universe. These cosmic entities possess immense gravity. This gravity is so strong that nothing, not even light, can escape their grasp. Imagine a place where the fabric of space-time is infinitely warped. That is the essence of a black hole. Our understanding of black holes stems from the groundbreaking work of Albert Einstein. His theory of general relativity revolutionized our view of gravity. Einstein showed that gravity is not a force, but a curvature in the fabric of space-time. This curvature is caused by the presence of mass and energy. Black holes are extreme examples of this curvature. They are regions where massive stars have collapsed under their own gravity. This collapse creates a singularity. A singularity is a point of infinite density and zero volume. The boundary around a black hole is called the event horizon. Anything that crosses the event horizon is forever trapped within its gravitational pull. Black holes are not cosmic vacuum cleaners, though. They only consume matter and energy that venture too close. Before Einstein, gravity was understood in Newtonian terms. Newton described gravity as a force acting between objects with mass. However, this theory couldn't explain certain astronomical observations. For example, the orbit of Mercury deviated slightly from Newton's predictions. Einstein's theory of general relativity provided a more complete picture. It showed that gravity is not a force, but a consequence of the curvature of space-time. Massive objects create a dent in space-time, much like a bowling ball placed on a trampoline. This curvature dictates the motion of objects around massive bodies. It's not that Earth is being pulled towards the Sun. Instead, Earth is simply following the curvature of space-time created by the Sun's mass. General relativity also predicted the existence of gravitational waves. These are ripples in space-time caused by the acceleration of massive objects. These waves travel at the speed of light and carry energy away from the source. One of the most important concepts in understanding black holes is the Schwarzschild radius. This radius, named after German physicist Karl Schwarzschild, defines the point of no return around a black hole. Imagine compressing the Earth into a smaller and smaller sphere. As Earth shrinks, its gravitational pull becomes stronger. At a certain critical radius, the escape velocity from Earth's surface would equal the speed of light. This critical radius is the Schwarzschild radius. For Earth, it's about the size of a marble. For an object to escape the gravitational pull within the Schwarzschild radius, it would need to travel faster than light. Since nothing can travel faster than light, anything that crosses this boundary is trapped forever. The Schwarzschild radius marks the event horizon of a black hole. It's a sphere around the singularity beyond which we cannot observe any events. Any information about an object that crosses the event horizon is lost to the outside universe. Section 4. Stellar demise, the birth of a black hole. Black holes are not cosmic oddities, but rather a natural consequence of stellar evolution. Stars are cosmic furnaces that fuse hydrogen into helium in their cores. This nuclear fusion releases enormous amounts of energy, counteracting the inward pull of gravity. However, stars have a finite lifespan. Eventually, they run out of fuel in their core. When a massive star, at least 3 times the mass of our Sun, exhausts its nuclear fuel, it can no longer support itself against its own gravity. The core collapses rapidly, reaching incredibly high densities. This collapse triggers a shockwave that blasts the outer layers of the star into space in a spectacular explosion known as a supernova. What remains is a stellar mass black hole. These black holes, typically a few times the mass of our Sun, are scattered throughout galaxies. They are remnants of massive stars that have lived out their lives and met a dramatic end. Section 5. Supermassive giants, the Hearts of Galaxies. While stellar mass black holes are fascinating, supermassive black holes reside at the centers of most galaxies, including our own Milky Way. These behemoths are millions or even billions of times more massive than our Sun. The formation of supermassive black holes is still a subject of active research. One theory suggests that they formed in the early universe from the collapse of giant gas clouds. Another possibility is that they grew over time by accreting matter from their surroundings. These black holes play a crucial role in the evolution of galaxies. Their immense gravity influences the orbits of stars and gas clouds, shaping the structure of the galaxy around them. The energy released as matter falls into these black holes can also trigger star formation and influence the overall activity of the galaxy.